Hello everyone, welcome to my channel. In this lecture, we will discuss about the adsorption of water vapor with the help of Aspen adsorption. In this lecture, we will discuss the adsorption of water vapor with the help of Aspen adsorption. Uh, we suppose we have a feed stream which consists of ethanol and water vapor. This stream is in the gaseous form. The ethanol, the feed consists of 81.8% ethanol and 18.2% water vapor. The feed molar flow rate is 5.2 kilomole per hour and the pressure is 379 kilopascal. The feed temperature is 440 Kelvin. We will use the zeolite adsorbent in order to remove the water vapor from ethanol water mixture. So we will use spherical zeolite. Here this is a paper, and in this paper they have used zeolite 3A in order to remove water vapor. They have used pressure swing adsorption process. But in this lecture, I will just use one bed column in order to remove water vapor from ethanol water mixture. This is a paper. This is the fluid composition, flow rate, and temperature. Uh, mm, this is a paper. Here you can see this is a paper separate. So in this paper, they have studied the pressure swing adsorption process in order to remove the water from ethanol water mixture. So here you can see they have used the pressure swing adsorption process. If you don't know about the pressure swing adsorption, you can check the video about the pressure swing adsorption process in the description of this video. They have used two bed column one, bed one, and bed two, bed number two. So in the pressure swing adsorption process, when this bed acting is when adsorption is taking place in this bed, then at the same time this bed will be regenerated. And after a certain time, when saturation occur in this bed, we will close this wall, and we will redirect the flow rate to this bed. So after a certain time, adsorption will take place in this column, and this will be regeneration will take place in this column. So this is a pressure swing adsorption process. Here, this is the waste wall. So this is usually used in order to for blow down purpose, in order to remove pressure from beds, and this is for the pressure equalization. This is usually used for the pressure equalization process, and this is the product wall in order to get the product composition. So you can use this wall. This is the product wall. But in this lecture, I will use a single bed of zeolite 3A in order to remove the water vapor from the ethanol water mixture. So first of all, we will open the Aspen adsorption. Aspen adsorption. Aspen adsorption. We will add our component. So we have go to the component list, click on configure property, click on use Aspen property system, click on edit using Aspen property. So now we will, from the Aspen adsorption, we will go to the Aspen plus, and we will put the component in the Aspen plus. And from the Aspen plus, we will add our component to the Aspen adsorption. So actually, we will add our component from the Aspen plus to the Aspen adsorption, because there is no existing component in the Aspen adsorption. So therefore, we will go to this one plus. So this is this one plus. Now we will go to the component. We have two component. One is the ethanol, and the other is water. Ethanol and water. Now click on the next, and we will use now this is the equation upstairs. So we can use various equation of state at different on your problem, but in this case I will use the Finn-Robinson equation of state. You can use the NRTL or other property package for your problem. Here I am using the Finn-Robinson equation of state, so it will determine the various property of the component. So click on next, click on OK. Now go to the Aspen adsorption, click on OK. Go to the Aspen plus again and click on yes. Go to Aspen adsorption again. So now now click on default. Here you can see this is the water molecule. So that means that component will present in this default portion. So double click on that and these are the component. So from the S1 plus I've added the component from S1 plus to the S1 adsorption. Here you can see now we will add the component. So double click on this one, double arrow. So and click on OK. So we have added the component from the S1 plus to the S1 adsorption. Now after that we will make a process sheet for the adsorption of water vapor. So this is usually a dynamic problem. Here we will study the behavior of bed with the help of time. So actually this is a gas dynamic problem. This is a gas speed. So this is a gas tube which consists of ethanol, water, and this is the bed. So in this bed there will be there will be zeolite 3A, spherical zeolite 3A will be present in this bed, and this is the product gas. So here you can see this is the product gas. Now connect the feed with bed and product with bed. So connect feed and product stream with the adsorption column. So click on this connection and gas material connection. This is a gas dynamic problem. So connect the feed stream with the adsorber and connect the adsorber with the product stream. Okay. Now specify the feed. We will double click on the feed. So click on specify. Now by default the flow rate of the feed is in kilomole per second and the it is free. So here you can see in the problem the feed molar flow rate is 5.2 kilomole per hour and this is fixed feed flow rate. So this is a fixed 5.2 kilomole per hour. Here you can see 5.2 kilomole per hour and this is in kilomole per hour. So first of all we will select the unit kilomole per hour, this one, and it is 512 kilomole per hour, and this is fixed. Here you can see that this is the fixed feed. The composition of ethanol in the feed stream is 81.8%. Here you can see 81.8%. So 0.818 and remaining is water. So it will be 0.182. 0.182. So this is the percentage. This kilomole per kilomole per, this is usually percentage. So the percentage of component in the feed stream. So now this is the 0.182. The feed pressure is 379 kilopascal. So specify the feed pressure. So the unit will be in kilopascal. So here you can see the kilopascal, 379 kilopascal, and the temperature of the feed is 440 Kelvin. So here we will check it, 379 kilopascal. Okay, now close this one. We have specified the feed stream. Close this one. Now we will click on the bed. This is the adsorption column. So you can rename block. So you can rename this one like adsorber. Adsorber. So this is the adsorber or adsorption column. And you can also rename this stream like this is a feed. Suppose you can rename like this is the feed. Okay, and this is the feed stream, and this is the product stream. So right click on the product stream, click on the rename block, and this is the product. product stream. Click on OK. Okay, this is the feed and this is the product stream. Okay, this is stream number one. The feed stream is stream number one. The product stream is stream number two. And this is the adsorption column. Now double click on the adsorption column. Here you can see the adsorber is in a vertical position and there is one layer of the zeolite 3A. So there will be one layer of adsorbent inside the adsorption column. If you put 2 in this place, it means that there are two layers of adsorbent inside the adsorption column. If you have a different adsorbent like activated carbon and zeolite, then you can put two in this place. So this will divide it into two section. The one layer will be for activated carbon and the other will be for the zeolite. But here we have one type adsorbent which is zeolite 3A. And the dimension, it is in one dimension in the z dimension. Here you can see this is in the direction. So this is in one dimension. Okay, and the adsorbent layer. So you can rename this one like you can rename like the adsorbent layer. So zeolite, zeolite 3A adsorbent. So, okay, Zeolite 3A adsorbent. Now click on this adsorbent layer, and here you can see this is a general, the discretization method. So in this case, we will use the discretization method UDS1, the upward difference method, and the number of node will be 20. You can change the number of node. You can also select other like UDS2 or CDS2. So these are the discretization method. And click on the material momentum and material balances. So this is the convection and the momentum balance is argon. So you can use the Karman-Cousins equation, Darcy equation, Brock-Flummer equation. So it depends on your problem. So I'm using the argon equation in this case. And here you can see this is the convection or constant dispersion or estimated dispersion. If you have value about the dispersion, the dispersion of component, so you can add the dispersion value. You can click on this one. If you have estimated the dispersion value from your calculation, you can also click on this one. I will use the convection only. So this problem will work only on convection process. And the kinetic model, here you can see the film model. The film model actually it shows the information about the film which is formed surrounding the adsorbent. So in liquid process, actually, is sometimes the water or the fluid make a layer around the adsorbent. It can be the fluid film model or it can be the solid model assumption. Here you can see, so I will use the solid for the film model assumption. I will use the solid. The kinetic model assumption, it can be linear or the quadratic or the macro or micro. If there is some adsorbent consist of the macro force and micro force. So if your adsorbent consists of micro and macro force, then you will use this one. I will use the lump resistance, and the form of the lump resistance model is either linear or quadratic, but here I will use the linear. The form of the mass transfer coefficient is constant. It can be estimated or constant. So you can estimate the mass transfer coefficient from various equations about the mass transfer. There are various equations from which you can calculate the mass transfer coefficient, like Fick's law of molecular diffusion and other diffusivity. From diffusivity, you can also calculate it. Similarly, from Knudsen diffusion and molecular diffusivities, you can calculate these mass transfer coefficient. But here, my mass transfer coefficient is constant. I know the value of these mass transfer coefficient for ethanol and water. Therefore, I will keep it constant. Now this is the energy balance. So this adsorption column will take place at a constant temperature. There will be no temperature changes. There will be no temperature change. The temperature sometime in reality the temperature changes because when the adsorption taking place, then at that case energy can be removed and the temperature inside the adsorption column can be increases. So similarly, when the gas molecule attached to the adsorbent surface, then at that case, sometime heat can be increases. So in that case, you can use the non-isothermal model. But here I'm using the isothermal, the energy balance assumption. I'm using the isothermal assumption for this case. If you have reaction, for example, if some reaction is taking place inside the adsorption column, then you can you can add your reaction. But there is no reaction taking place in this adsorption process. Simply the ethanol and water component will pass through the adsorption column. Water molecule will attach to the uh, zeolite, zeolite particle, and the adsorption of water will take place inside the adsorption column. There will be no reaction between the zeolite and the water molecule, so there is no reaction in this case. And here this is the specify. Now click on specify, and here now click on this one. I have only one this one isothermal. So there are various isotherm. Isotherm are actually floats. Isotherm actually these are the curves which we can float at constant temperature. Like Langmuir isotherms, the Freundlich isotherms. There are various isotherms which are actually we are using these isotherm for our adsorption during our adsorption experiments. And these isotherms actually show us the adsorbent uptake, so that how much molecule is attached to the adsorbent particles. So, for example, if we have 1 kilogram adsorbent and there is 10 milligram water is attached to the 1 kilogram adsorbent, then its uptake will be 10 divided by 1 kilogram. So 10 milligram of water molecule divided by 1 kilogram of adsorbent. So these are the they show us these isotherms actually show us the adsorbent uptake, and these isotherms can be plot from the adsorption equilibrium study. And adsorption equilibrium study can be achieved from adsorption kinetic study. So first of all, you will do some experiments. You will study the kinetic of the adsorption process, and from the kinetic study, you will then find the equilibrium. You will the equilibrium components, the equilibrium composition, the equilibrium uptake, and from these equilibrium composition, from these equilibrium concentration and equilibrium uptake, you will find the uh, you will plot the isotherms from equilibrium values. Because if you know about the linear plot of the linear isotherm, so it is actually can be made against CE divided by QE against CE. So CE is the equilibrium concentration and QE is the equilibrium effect. So from the equilibrium study, you can plot various isotherms. So in this case, my isotherm is the Langmuir 2. I will use the Langmuir 2 isotherm, and this isotherm is dependent. The isotherm will depend on the concentration. It can be depend on the partial pressure, or it can be depend on the concentration. So I'm using the concentration. These concentration or partial pressure are actually the driving force for the adsorption process. So due to the concentration gradient, adsorption will take place inside the adsorption column. Okay, link here to okay, the energy balance is isothermal. There is no reaction. Click on specify. Now the bed height, the bed diameter. So what will be the height of my adsorption column? So this is the HB is actually the height of the adsorption column. The DB is the internal diameter of the adsorption column. So the height of the adsorption column here you can see. I will put value from this paper. this one like the bed length. This is actually the bed length or bed height. It is 7.3 meter. So 7.3 meter. 7.3 meter. So the height of my adsorption column will be 7.3 meter. And here you can see the diameter, the bed diameter. It is actually the inside diameter, the internal diameter of the adsorption column. So this is the 2.4. 2.4 is the 2.4 is the internal diameter of the adsorption column. The intraparticle voidage. So, and the interparticle voidage, these are the porosity, and these are the porosity. This is so one is the porosity and other is the watt fraction. So these are shows the porosity of the bed and the porosity of the particle and the watt fraction of the adsorption column. The interparticle voidage in this case is the interparticle voidage is 0.4. So 0.4. 0.4. And for most of adsorbent, the interparticle voidage or the uh, word fraction of the column is mostly 0.4. It is mostly from 0.4 to 0.45. And the intraparticle voidage, this is the value for intraparticle voidage is 0.63, 0.63, 0.63, 0.63. Three. Now this is the density of the this is the bulk density of the adsorbent. So what is the density of the zeolite 3A? Actually, zeolite is adsorbent. In this case, zeolite 3 is adsorbent, and its densities you can search the density of adsorbent from online sources or various research papers. So this is the adsorbent. The density of the adsorbent. So the density of the adsorbent, the bulk density of the adsorbent is this one. So 729.62 kilogram per cubic meter. So the density is and the particle radius. So this is the radius of the adsorbent particle radius. So what is the radius of the spherical zeolite 3A? So this is the radius of the adsorbent particle. So the radius of the adsorbent is here the adsorbent particle radius. It is 0.0015875. So 0.0015 875. 0.0015875, and the adsorbent in this case it is spherical, so the sphericity of the adsorbent is 1. So if the adsorbent is not spherical, then its sphericity will be less than 1. So this is the mass transfer coefficient here. We have already discussed that the mass transfer coefficient is constant. The value for the mass transfer coefficient are given. So the mass transfer coefficient for the ethanol and water. The mass transfer coefficient for ethanol and water. So the mass transfer coefficient here, this is for ethanol, 1.9960. This is for ethanol, and its unit is 1 divided by second. So this is for ethanol, and for water, the mass transfer coefficient is, and for water is, this is for water. Now the isothermal parameter. So we have used the Langmuir 2 isotherms, and the various parameters of the Langmuir 2 isotherms are these are the various isothermal parameter of the Langmuir 2 isotherms. So actually there are three parameters for ethanol, parameter number 1, IP1 for ethanol, IP2 for ethanol, IP3 for ethanol, IP4 for ethanol. There are 4 parameter for ethanol and 4 parameter for water. Because when the water molecule is adsorbing on the adsorbent, then it will release some energy. It will show some affinity toward the adsorbent, and there are these various parameters are actually calculated from the linear plot of the Langmuir isotherms. These are the isothermal parameter, and these mass transfer coefficient, actually these are calculated from various mass transfer equations. You can calculate these mass transfer coefficient. These can be calculated from diffusivity, Knudsen diffusion, etc. Isothermal parameter for the ethanol. So here you can see this for the water. Isothermal parameter 1 for water, isothermal parameter 2 for water, and so on. And isothermal parameter 1 for water is this one. So 1.9064 for water, 10 raised to power minus 1.9064 multiplied by 10 raised to power minus 7. Similarly, isothermal parameter 2 for water is 6242.13, this one. Isothermal parameter 2 for water is this one. So 6242.13. Isothermal parameter 3 for water 1.7874. 1.7874 multiplied by 10 raised to 4 minus 5. This one. And isothermal parameter 4 for water is same as isothermal parameter 2 and 4 are is same. So 6242, this one, 6242.13. Now isothermal parameter 1 for ethanol. Here you can see isothermal parameter 1, 2, 3, 4 for water is, for ethanol is 0. So for ethanol is 0. Now, okay. Now the flow direction is 0, 0. Okay. Close this one. Close this one. Now click on the product stream. Click on product stream. Click on specify. Now we will let them free. These will be free. Aspen adsorption will be calculated. This value. This will change with the passage of time. Okay. This is the mole fraction of ethanol in the product stream. So what will be the mole fraction of ethanol after the adsorption? So after the adsorption process, and what will be the mole fraction of water vapor after the adsorption process? So in this case, the as we know that the zeolite 3 adsorbent actually usually remove water vapor. It is used for dehydration purpose. So it is actually removing water molecule from stream. So the water molecule, the component, the mole fraction of water in this product stream will be very small, because a lot of the water molecule will be adsorbed by the adsorbent which is present in this adsorption column. And when water molecule is adsorbing by this adsorbent, then the concentration of the ethanol in this product stream will be increases with the passage of time. So it will be increases with the passage of time. We will check this one. Okay, now click on product, click on specify. So in this problem here you can see This is here you can see this is the ethanol percentage in the product stream is 98%. So and water is very very small. Here you can see this here there is at about 18% water, and here you can see there is about 1% water. So water is mostly removed by the adsorbent. Mostly water is removed by the adsorbent, which is zeolite 3A. So we will specify the composition. So the composition of the ethanol in this case is 0.9885, 0.9885, 0.0115, 0.0115, 0.0115. Here you can see 0.0115, and the flow rate is of the product stream is 473 kilomole per hour. But here I'm just leaving this free, and the this is actually the so thermal process. There is no heat is neither generating nor absorbing in this case. So the product stream temperature and the feed stream temperature is equal. So this is we will use 440 because the feed stream temperature is also 440. Okay, and the pressure here you can see we have used the argon equation, and the pressure drop will take place inside the adsorption column. So this will be not fixed. We don't know that whether this is 3 bar or some other pressure. So the pressure will be we use in the kilopascal, and the pressure will be changes because we don't know the pressure. So we will keep it free. Okay, this is okay. This is pressure is free because we don't know it will changes just like the flow rate. And these are we have defined. We want suppose 1.15% water in the product stream, and we want mostly ethanol in the product stream. So this means that most a lot of water molecule is absorbed by the adsorbent. So now water molecule is attaching to the zeolite 3A. It is because it will depend on the surface and the functional group which is present on the surface of the zeolite 3A, and you can determine the functional group by the FTIR and XRD characterization methods. So with the help of XRD and FTIR, you can find the functional group of the zeolite 3A. It may be due to the functional group. Due to the functional group of the zeolite 3A, the water molecule is attached to the adsorbent. It can be due to the functional group or uh, some other uh, some other forces. It can be physiosorption or chemiosorption. So it can be determined. The physiosorption, chemiosorption can be determined from the enthalpy of the adsorption process. So okay, now close this one. Close this one. Now here you can see over specified. The simulation is over specified by 20 initial variable. Okay. Now we will go to this one. Click on initialization. Okay. Click on this one, click on this one, click on initial. So here you can see the mole fraction of the ethanol in the first layer within the first element of the adsorber. So at the start there will be no ethanol and no water inside the adsorption column, so we will put just very small value like this one. Very very small value. So suppose there is very very small or negligible ethanol and water at the beginning of the adsorption process. Okay, now close this one. Click on initialize your results. Now it is ready. Close this one, close this one. Click on the initialization. The run is complete. Okay, now we will plot the breakthrough curves. So go to this new form, click on this one and plot the breakthrough curves. Break, breakthrough curve. Okay. Now double click on the product because we want the composition of the ethanol and water in the product stream. So click on the results and this is ethanol, drag and drop ethanol, click on water, drag and drop. This is the composition of water in the product, this composition of ethanol in the product stream. Okay, here you can see this is the breakthrough curve. This is the time. So with the passage of time, the composition of ethanol and water in the product stream will be determined with the help of this graph. And this graph is called the breakthrough curves or breakthrough graph. We will run now for how much time we can run the simulation. So we can run the simulation for when the exhaustion or the saturation occurs. So we will just assume value for this problem because we don't know this that how much after how much time the adsorbent will saturated by the adsorbate. So adsorbate here, the adsorbate is the water and the ethanol molecules. Click on this one and from this go to the dynamic and we will pause our simulation after 5000 suppose 5000 second 5000 second. You can add other value like 3000 second 400 depend on your problem. Click on OK. Now you can change this axis like double click on this one. My simulation will run from 0 second to 5000 second. It will stop at 500 at 5000 second. The time window is 5000 and the grid interval will be suppose 500. Click on OK. Now click on the dynamic. So here you can see the simulation starts. It will stop at 5000 second. And these are the breakthrough curves. This layer is for the water and the green one is for the ethanol. So let's check it. It will take some time. It will stop after 5000 second. So we will from this graph. So this is the breakthrough graph. Now the breakthrough graph, the Aspen adsorption making the breakthrough curves. So now it will take some time. Here you can see you can stop your simulation at any time like this. This is the stop button. You can stop simulation, but here I will let's check it. 4000. Now 4647. Okay, the run is complete. Click on OK. This one maximize this breakthrough curve. Here you can see 5. This is the distance between 2 points. This here you can see the simulation stop at 5000 second. And here you can see this is the methanol concentration in the product stream. It is decreases with the passage of time. Here you can see it decreases with the passage of time. And the in the water molecule, the concentration of water in the product increases after 3000 seconds. So here you can see after 3000 seconds the methanol concentration in the product stream decreases and the water concentration in the product stream increases. But after here you can see after 3500 seconds it become constant. So you can so now right click on the graph, click on the property, click on the map axis, click on one for each, click on OK. So here you can see at the start, this is the start of the adsorption, and the adsorption taking place at start at 5000 second. So at the start, the mole fraction of ethanol, this is for ethanol and this is for water. At the start, the mole fraction of ethanol in the product stream was 1. At the beginning, the mole fraction of the ethanol was quite high in the product stream. It means, and at the start, there was no water, or there was very small concentration of water molecule in the product stream. It means that it means that up to 3000 second, the adsorption of water molecule was taking place inside the adsorption column. Here you can see, but after 3000 seconds, the concentration of water molecule, the concentration of water in the product stream suddenly increased, and to the it reached to the feed stream. Here you can see the feed in the feed stream, the concentration of water was about 18%. So after 4000 seconds, the composition of water molecule, the composition of water in the product stream become equal to the feed stream composition. And this is the breakthrough time. Here you can see when 95% of the product stream, when the here you can see the in the start, the zeolite molecule is absorbing the water molecules. This here you can see, this line show that lot of the water molecule is attaching to the adsorbent, which is present inside the adsorption column, and mostly the ethanol is coming out in the product stream because there is no water molecule present in the, or very small water molecule is present in the product stream. But after a certain time, the concentration of water in the product stream increases and the concentration of ethanol decreases. And here you can see after 4000 seconds, the concentration of ethanol in the product stream become equal to the concentration of ethanol which is present in the feed stream, which is 81%. Here from you can check. So actually this shows the breakthrough curves, and the breakthrough time, it is the time when the when the product concentration reach to 95% of the feed concentration. So the feed concentration, in the feed, the concentration of ethanol was 80%, 81%. Here you can see in the feed it was in the feed the concentration of ethanol, this here you can see this one. In the feed, the concentration of ethanol was 81%. Here you can see. So when this concentration, when this 81, the feed concentration reached to 85, when the product concentration reached to 85% of the 95% of the feed concentration, then at that time you can find the breakthrough time. So you can find the breakthrough time from this x-axis. This is the time. So here you can see this is the water. The water molecule is not present. It slightly increases, and it increases, and here from this point you can calculate the breakthrough time. Similarly, for the breakthrough time can be calculated for the ethanol from this curve. So you can check the breakthrough time. What is the breakthrough time? You can study the breakthrough time in various research paper on or from online resources. Actually this is the water. Okay, here you can see. So here the water, this is the feed. The water is 18%. So 95%, 90. If you take 95% of the 18%, so it will give us about 17.5 or 17.6. And now go to 17.5. If you another if you want to find the breakthrough time, you can just multiply your multiply the composition of the water which is present in the feed, multiply that composition by 95%. So if we multiply 18 by 95, you will get 17.5 or some other value. So 17, so let us just let's suppose 17 point, the value occur when we multiply 18% by 95. Let's check it. Suppose the feed consists of it was about 18. Here you can see the feed how much it was. 18.2. 18.2 multiply by 0.95. So 17.29. 17.29. So 17.29. This is 17.29. So this is 17.5. Here about this, mark this position for water 17. Now go to this 17.2 and go to the water. So this about 36 are about the 35 3600. So at 36, after 3600, after 1 hour, the adsorbent will exhaust it. The saturation of adsorbent will occur after 1 hour in the adsorption column. That can be calculated from this. So once this time reach, you will purge, you will regenerate your adsorbent in order to start the next cycle for your adsorption. So this is was about the breakthrough curve. Now you can calculate the solid loading. Click on this one. Suppose the solid loading, for example, the adsorbent loading. Adsorbent loading with the passage of time. Suppose the time was 5,000. The grid interval is 500. Suppose the time axis was 5,000. Okay. Now, how can we calculate the solid loading with the passage of time? So you can calculate. Click on this one. Click on this one. Click on results. And here you can, from this table, you can calculate. This is the concentration of ethanol in the bulk stream, concentration of water in the bulk stream. Here you can see this is the mole fraction of ethanol in the element, mole fraction of ethanol. So here you can see the solid loading. The solid loading, the solid loading. Suppose we calculate the solid loading for water. So this is point number one, point number two for water, point number three for water. So actually the point one shows the base of the adsorption column, and and the point 10, here you can see the total number of point here 20. So this 20 is the top of the adsorption column. This show the top of the adsorption column, and 10 show us the middle of the adsorption column, and the point 11 show us this point, and this point 1 shows the base of the adsorption column. This point, the base of the adsorption column. This is calculated. This is shown by point 11. This is calculated by point 10, and point 20 is calculated. The point 20 shows this top of the adsorption column. So now we calculate the solid loading of the this. Now we calculate that what is the uptake of the zeolite. So how much we calculate? Actually, we mean that how much kilomole of water molecule is attaching to the zeolite adsorbent, which is present inside the adsorption column. So this is point number one. How much water molecule will be attached to the adsorbent, the adsorbent which is present at the base of the adsorption column. So drag and drop this one. Now 10 point number 10, point number 10, here you can see this point number 10, this one. This was the middle of the adsorber. 10, 20. This is point number 20. So here you can see this green line shows the base of the adsorber. The base of the adsorber, this point. This is the base of the adsorber. And this is the middle of the adsorber. And this is the top of the adsorber. So the saturation will occur first, the particle, first of all, the saturation will occur in this place. And after certain time, saturation of the adsorbent will occur. And after certain time, the water molecule will attach to the zeolite, which is present in this place, in this top, in this top position. So this graph actually shows this information. This green show the base of the adsorber. So in the base, so the particle of the zeolite which is present in the base, in the bottom of the adsorber, will saturate firstly. So it will saturate after 500 seconds. And after and the middle and the zeolite particle which is present in the middle of the adsorption column will be saturated after 2500 seconds. From this you can see this is the equilibrium, and the zeolite which is present at the top of the adsorption column will saturated after 4500 seconds. You can also calculate this graph for the ethanol. So here you can see the water molecule is attaching to the zeolite particle, and this shows the uptake, the adsorbent uptake, that how much water molecule is attaching to the adsorbent which is zeolite, and this show us the uptake. So you can calculate the uptake from your experimental data. You can calculate an Excel sheet or some other programming, but Aspen adsorption is very accurate, and you can calculate the adsorbent uptake in very less time in this simulation, in this simulator. Similarly, suppose we calculate the adsorbent uptake for other molecule like adsorbent uptake for ethanol. ETH mean ethanol. So this one 5000, interval is suppose 500, time window is 5000. Okay. Now just like the same case, this is the ethanol. Ethanol in the middle, and ethanol at the top. How much ethanol is absorbed at the top? Now maximize this one. Click on the property for each. Click on OK. So here you can see very small or no ethanol. No ethanol is absorbed by the adsorbent. Here you can see no ethanol is absorbed, and mostly the adsorbent absorbed the water molecules from the stream. Here you can see it is zero, zero. So it is very small R0. Here you can see marker and line. So The value are very quite near to each other, therefore it gives us the straight line. Here you can see. Now if we change the time axis to suppose 550, here you can see you can also like this one. Okay, so mostly water is adsorbed. Okay, now you can also calculate other plot. Suppose I'm calculating some other plots like the pressure. So click on this one. Okay, click on this profile plot, pressure versus height. How pressure is changes inside the adsorption column. So click on OK, pressure versus height. So now right click on this one, go to the profile variable, click on this one and profile, define your parameter. So the pressure and height of the adsorber, of the adsorption column, or height of the zeolite. Okay, okay, okay. This is the pressure. This is the okay. Now click on this profile variable. So click on find variable. Find variable. Click on find. So on my x-axis, the I will plot the height of the adsorber on the x-axis, on this x-axis, and pressure will be on the y-axis, because when the height of the adsorber changes, the pressure inside the adsorption column will also changes. It will decreases as we go from bottom to top of the adsorption column. And actually, it was calculated by the by the pressure drop equation. It is organic, from organic equation we calculated. So the pressure, click in and go the pressure. So here we will check the pressure. Here you can see the point, the variable first point, gas velocity, pressure within the element. So this is, suppose this, drag and drop this one. Now remove this point. This is the pressure of the top, but I will remove this one and I will replace 21 by star. So this star actually mean the pressure for the whole column. It will show the pressure change for the whole column. Okay, okay. Now find, click on find variable, click on find and height. So select height from this table. So we will close this one, calculate height from this. This is the axial distance. This is the height. It shows the height here. This is the 7.3 is the total height. You can see. So drag and drop this one, and 0.20 will be replaced for. So this is the total height. So the pressure change along the whole height. How pressure will be changes along the whole height. Okay. Now the height will be plotted on the x-axis, and the okay, and the pressure will be on the y-axis. Okay, so we will remove this one. There is some, this is height and this is the pressure. So we will, there's some error. Click this one, remove this one. Now pressure. So suppose we, first of all, we calculate height. Height, height of the adsorption column, and this is the height. Here you can see height. So drag and drop. So I will drag and drop another height. This one. Okay. Close this one. Again, click on find variable. So here you can see it is time taking. So suppose just this one. Drag and drop. Okay, this one. Click on this one and now drag and drop. So okay, replace this with star, and the height will be on the x-axis. Okay, now select another pressure, pressure, and now go here and we can also search pressure in this search bar. So let's check the pressure of the adsorption column. So gas maximum solid loading enthalpy. This is the pressure. Drag and drop. Replace this by star. Now the pressure will be plot on the y-axis. Okay, if you give timing to your plot, you can also select timing option like this one. Click on time, specify time. So this adsorption is for 5,000 seconds. So after 1,000 second, how the pressure will changes. After 2,000 second, how pressure will changes. 3,000 second, 4,000 second, and 5,000 second. Click on OK. So here you can see this is the height. So as we go from bottom to the top of the adsorption column, the pressure inside the adsorption column will be decreases. So this is the top. So and this is the 5,000 second, and this is after, this is 0 and this is at 0. The pressure at the beginning of the adsorption process, the pressure was constant. This was the pressure. From here you can see the pressure. Here you can see this is 3.79 kilopascal. And after 1,000 second, the pressure, here you can see, after 1,000 second, the pressure was this one. This was the pressure. The pressure was decreased. It is because after 1,000 seconds, the molecule travel some distance, and the pressure inside the adsorption column decrease as we go to some height. And here you, after 3,000 second, this one, and after 5,000 seconds, so the pressure decrease. So the pressure decreased at 5,000 seconds. The pressure was very small as compared to the other time. So this is actually the timing. The timing. This is the time. So as the time, so here you can see as the time increases from zero. This is zero. This is zero, and this is 5,000. This one. So as the time increases, the pressure decreases. So it is because when time increases, the molecule travel some distances. So therefore the pressure decreases. It is absorbing more and more water molecule absorbing to the adsorbent. So the number of molecule inside the adsorption column decreases. So its pressure also decreases as we go from bottom to top. So this was the okay. You can also plot some other graph as you wish. So suppose I'm plotting some other graph like X, Y, Z graph. Okay, so you can plot like click on this one, go to the property like this one, like loading, adsorbent loading with height. So suppose this is loading, point variable, adsorbent loading. Suppose I'm plotting the gas velocity, the gas velocity. This is the gas velocity. We'll rename this one gas velocity. Gas velocity on the y-axis, suppose, and the height on the x-axis, height on the x-axis. This is height on the x-axis. I'm plotting another like pressure, pressure. I'm also plotting this on y-axis. So it is the pressure, drag and drop, the pressure on the y-axis. Okay, you can also give time, but it will become very complex. So just click on OK. So here you can see with height, pressure decreases and the gas velocity is this is the gas. It is nearly constant. Here you can see it is nearly constant. So this was all about that how can we plot graphs and how they adsorption, how the zeolite absorb the water molecule from the ethanol water mixture. Thank you very much for your attention. If you are new to the channel, please like and subscribe.